see my screen?
Yes, we can see your screen, Professor.
Okay.
Okay.
So,
yeah,
okay.
I give you the mic, Professor. Thank you so much.
Lesson
Hmm?
the neutrino and stuff. No, guys, no. I think that one was better. Astrophysics looks yeah. So that's my quote.
Okay. Is everyone you're ready? I can begin.
We are ready.
Okay, just
Oh.
go like this. Okay, it's a full screen now. Is good for you? The resolution is perfect for you?
Yes, we can
Okay.
see. You probably can't see us anymore, but we can see you and your screen.
Okay, maybe I should I don't know, stop my camera, just keep the slide maybe.
Oh yeah, it's fine.
It's like I just have to stop the camera and keep only the slides.
But you can't do both. At least we will still we are able to see you and your screen, but you are not able to see us. So at least we can. It's fine for us to see you and the screen.
Okay, perfect. So let's go like this. Just have to. I'm sorry, there was a baby close to me in the next room.
Oh.
He's crying sometimes. Okay,
Okay.
so I would talk about neutrinos. I don't know if the students have ever heard about neutrinos. I assume that maybe in your own lectures, in your own reading, you have encountered neutrinos particles. And the first thing I want to say is neutrinos in the standard model. I think and I hope that everybody have already seen this picture. This is the particles chart. All the basic particles we have are represented in this chart. In this chart, I don't know if you can see mine. I'm sorry. I wanted to see my pointer.
No, we can
Even
see
myself, I don't
now.
see it. So it's quite difficult. Just try to understand, to listen to me. And we have in particles, in particle physics, we have first of all two. We can separate. We can divide the particles in two subsets. The first one is what we call the bosons, and the second is what we call the fermions. Depending on the spin, I don't know if you heard about a spin. A spin is a particle property of particles, and according to the value of the spin, you can then divide the particles in two groups: bosons in a way, and fermions. Bosons have got integer spin, and fermions have got half spin. So in these charts, what you see first on the first line, you see what we call the quarks. We've got six quarks. Okay, U, C, T, D, S, and B. They are quarks. Okay, and just below you have another line where you have the electron, the muon, and the tau. Then we have the neutrinos just below. For each lepton, because electron and muon and tau and neutrinos, they form a subset that we call leptons. And we have six leptons, and they come into families. This means that for each charged lepton, we have a neutrino which is associated to this lepton. For the electron, we have the electron neutrino just below. For the muon, we have the muon neutrinos, and the tau, we have the tau neutrinos. The electron, the muon, and the tau are charged particles. Neutrinos have got no charge. And in red, you can see that we have three types of neutrinos, and we used to say flavors. So we have three neutrinos flavors. Okay. The same way we have electron, mu, and tau, the same way we have a neutrino for the electron, a neutrino for the muon, and a neutrino for the tau. We have three flavors or three types of neutrinos. This is the first thing you need to know about neutrinos. They are fermions, they are leptons, and they are what we call the non-charged leptons. And then some particle things need to be known about neutrinos. As I said, they are neutral, they have no electric charge, and they are the most abundant in the universe. Okay, you have more than 300 neutrinos per centimeter cube. This means that each second you have never noticed that you don't feel anything, you don't detect anything, but your body traverses each second by 10 to 14 neutrinos. This is huge, and this is something very important. And you may be aware that you can also classify particles what you call left-handed and right-handed, but there exists for neutrinos only left-handed neutrinos. This is something very special. Maybe it's not the time to go in deep for that. But what I want to say today, especially about neutrinos, is that when you see when you read a particle physics book, you will encounter what we call the standard model, which is the frame, okay, the mathematical frame that describes the interactions of particles. Okay, this is what you call the standard model. And this standard model, in the calculations, in the mathematics inside, we assume that neutrinos have got no mass. And all equations in this standard model, which describes particle physics, assume that neutrinos have got no mass. But a few years ago, we have, thanks to experiments, seen that neutrinos have got mass. And this is very decisive because this changes many things in our understanding of the universe. And we're going to see that. And the consequence of the fact that neutrinos have got mass, they can oscillate. This is what we call the neutrinos oscillation. What is oscillation? I will explain here before showing the next slide. Remember that I said in the first slide that we've got three types of neutrinos, okay? But what happens with neutrinos is very, very special. They are the only particles that have this property. This property is this. When you produce a neutrino, you produce a neutrino with a special flavor. We have three flavors. We have the electron flavor, the muon flavor, and the tau flavor. But it happens that when you produce a neutrino with a special flavor, for example, I produce the electron neutrino, okay? And then after some distance, you want to detect the neutrino, you produce it some kilometers away. And when you detect this neutrino after traveling this distance, it may happen that you detect the neutrino with another flavor different from the one that it had at the beginning. Sorry. I'm sorry. Just have a message. Give me 1 second. I just have to stop this call. Type maybe.
Okay, no problem.
Somebody's calling me. I will call him back, but I just have to stop the call.
Okay.
Okay. So they oscillate. This means I produce my neutrino with a special flavor and I detect it after some distance with a different flavor, different from the one it had when it had been produced. And this is very, very special. This is what we call the neutrino oscillation. Neutrinos change the flavor as they travel in the universe. And they can do this only if they have mass. And this is very, I mean, it's a problem for particle physicists, because we assume in our equations, in our calculation of the standard model, we assume they don't have any mass. So if they have mass, we have to rewrite almost all the equations of particle physics. And this is very exciting and very, very special. So how do we know that neutrinos have got mass? We know that because they oscillate. I will show you in another slide why. But now I want to show you how we detected, how we are sure now that they oscillate. If you take the sun is a star, okay? And as you know, in the stars, you have the fusion reactions, the nuclear reactions inside of the star, and they produce electron neutrinos, okay? The sun only produces electron neutrinos. And there was an experiment is still going on, is what we call the snow experiment. And before snow experiments, other experiments tried to identify, to detect the neutrinos emitted from the sun, okay? And as we know how the sun produces neutrinos, we are able, only by calculations, to predict the number of neutrinos that will go out of the sun and reach the earth. This calculation, this theoretical calculation, is possible. This is what we call the solar standard model. So we know the prediction. The prediction is just written here. You see SSM prediction. We know the prediction. We are waiting for 5 from 10 to 6 neutrinos per centimeter square and per second. This is the prediction. And this prediction works because it does not only predict neutrinos, it predicts many other things. And all the other things predicted by this solar standard model works. So we are very sure about this model, these calculations. And then many experiments tried now to detect neutrinos, to count how many neutrinos reach the Earth, and then to compare the number detected with the number predicted by the theory. Okay, this is what we do in experiments. And in this graph here in the right, you have different. The first, you have a group of histograms. Okay, we have 1, 2, 3, 4, 5 groups. The first group is another experiment. The second one is a different experiment, and so on. Okay, so each experiment, the four first groups of my picture here, you have experiments trying to count the neutrinos emitted from the sun. And in yellow, okay, for each group, in yellow, you have the prediction, okay? And as you can see, in the first 4 groups of histograms, the yellow one, the prediction, is always higher than the blue one, which are the experiments. This means that the number of neutrinos counted by the experiments is always below the expectation from the theory. Okay, the yellow one is always higher than the blue ones. So these 4 experiments were unable to find the same number of neutrinos as the one predicted by the theory. This was the case because we know that the electron neutrinos are the only electrons predicted by the theory, and the first 4 experiments were detecting only the electron neutrino. So they were sensitive only to one flavor, which is the electron neutrinos. So it seems that to them that from the traveling from the sun to the earth, some neutrinos have simply disappeared because the number measured is very low compared to the prediction. And then came the snow experiments. the main difference between the snow experiments and the other experiments is that the snow experiments was able to measure, was able to detect not only electron neutrinos, but also the other two flavors, the muon and the tau neutrinos. And then the miracle happened because when snow detected the three flavors, the number of neutrinos detected is matching the number predicted by the theory. Okay? So this means that when they traveled, the original neutrinos from the star, which is the sun, was only electron neutrinos, but from this travel from the earth, from the sun to the earth, they changed the flavors. Okay, so when you measure the three flavors, you find the number predicted by the theory. This simply means that while moving, they change the flavor, and this change of flavor is what we call the oscillation. Neutrinos oscillate. Okay, this is very special, and for this, the snow experiments obtained the Nobel Prize. Very, very decisive. And you can see this in all other experiments. We've got many sources, many origins of neutrinos. You can produce neutrinos in a star, you can produce it in beta decays, you can also produce neutrinos in the atmospheric interactions of cosmic rays, which interact in the higher atmosphere. They also predict neutrinos. And also in that case, when they wanted to calculate, to compare the prediction and experiments, you can see here in the right, the plot in the right, okay, that's the prediction in green is always higher than the measurement. And when they wanted to measure all the neutrinos at the same time, the prediction is matching the experiment, simply because neutrinos oscillate. So this is true now that neutrinos oscillate. Now I want to see you just some few calculations. Don't be scared. This means in mathematical frame, if neutrinos oscillate, this means that neutrinos as flavors are different from neutrinos as mass state. In mathematics, we say that mass eigenstates and flavor eigenstates are different, but they are connected by a matrix, and this matrix is what we call the PMNS matrix. It's for Pontecorvo, Maki, Nakagawa, Sakata. And this matrix is linking the flavors and the mass states. And you have many parameterization of this matrix. One of them is the V expression given here. Maybe I will say a few words if you have any question about this after. But what I want you to see is the bottom equation here. Okay, the last equation of this slide. Okay, the last equation on the bottom. If you see this last equation is giving you the probability that a neutrino with a specific flavor change into another flavor. And this probability, as you can see in this last equation, depends on the L is the distance, depends on the energy of the neutrino, and also depends on the difference of the square mass of the neutrinos. So if the neutrinos were massless, the square mass would have been 0. So as you know, that the sinus of 0 is 0. So we should see no oscillation if the mass were 0. But since we see the oscillations by the experiments, this now implies that neutrinos have got mass. And this is a very wonderful demonstration of the fact that the equation we have in the standard model are not satisfying, because we have to take into account the fact that neutrino oscillates. And if we take into account the fact that they oscillate, this implies that we have to take into account the fact that neutrinos have got mass. They are not massless particles. This is one of the most wonderful experiments and discovery of the last 10 years. And for this also, there was a second Nobel Prize for this demonstration. Then I'll give you some values. Remember that in this matrix, you've got many parameters. And what we do in physics experiments is to try to calculate these parameters. And in this list, you have the values as we have calculated from experiments of the different parameters that form the matrix, the PMNS matrix for neutrinos. Just for information, but you can find it in many particle data books. And now that we know that neutrinos have got mass, we know that they oscillate. The question is that this is few answers compared to many other questions we have about neutrinos. The first question is that still now, we don't know if neutrinos are their own antiparticle. You know that in particle physics, for each particle corresponds to an antiparticle. For example, you have the electron, which is negatively charged, and there exists, let's say, the opposite of electron that we call the positron, which has got the same things in terms of mass and other properties as the electron, except the value of the charge. The positron is just the electron which is positively charged. And this is what we call the antiparticle. But it seems it's still possible to neutrinos to be their own antiparticles, but we don't know yet. We have to check. We have to find out. And we also know, as you see, that in oscillation, the only thing we measure here, I'll come back, is the difference of masses. You see, delta m squared is just the difference between masses. This is from the oscillation expression. We have access only to the difference of masses. But what we want to know is the absolute masses. What are the absolute masses for the free neutrinos? We still don't know. And if we know the masses, the question is, what is the hierarchy between these masses? Among the free neutrinos flavors, which one is the more massive than the other ones? And in physics, in particle physics, there is something very important, is the CP symmetry. The CP symmetry is the fact that particles behave differently from antiparticles. And if neutrinos, they violate the CP symmetry, this means that neutrinos behave very differently from their opposite particle, from the antiparticles. This has got many consequences about our understanding of the universe. You know that when the universe began at the Big Bang moment, in the reality, according to the conservations of charges, okay, that you know, particles have been created the same time as antiparticles. And the quantity was the same to conserve the charge. But if you see the universe around you, if you see the table that you have in your front of you or your laptop, we have only particles. We don't see antiparticles. So it seems that when the universe was in its evolution, preferred particles instead of antiparticles. This is what we call the CP variation. So if this variation is also the case for neutrinos, this will tell us a lot about the universe, why we have more matter than antimatter in the universe. Very important question. And neutrinos, they are really very weakly interacting particles. It's very difficult to detect neutrinos. They traverse the universe, they traverse the earth, they traverse your body without interacting with anything. So they are very difficult to detect. And since they are so difficult to detect, to be detected, this means that the original neutrinos, which have been created at the beginning of the universe, are still traveling the universe. Okay? Because since they don't interact, the only way for a particle to disappear is to interact and to generate new or different particles. But when it doesn't interact, so this means the particle is just traveling the universe without changing its properties. So this means that if we are studying neutrinos, the original neutrinos that we call the cosmic neutrinos, if we're studying these neutrinos, since they are the same neutrinos which have not interacted at all from the beginning of the universe, these neutrinos have got a lot of information to tell us about the origin of the universe. Very important. And also, I said that we have three flavors of neutrinos. I said we have three simply because we have detected only three flavors. But there is no reason to have only three. Maybe there are more than three. And if there are more than three, this will 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 create new questions about the universe. Remember that in physics, when you find something, you discover something. Each discovery will bring new questions. Okay, so it's always interesting. That's why physics is endless, because each answer will bring more questions than the answer itself. So you see that we have many things here. I put this slide for you. I want you to look at the slides, to the many questions, and to pick up one question and to try to solve this question. And this is my way for you to ensure that if you solve one of these questions, you've got another prize. Okay, so this slide is for you. For those who want to have another prize, this is for you. Okay, so I want to tell you now just my last part about my work on neutrinos. Okay, and my work is what we call the double shoes experiment in English. So from the beta decay, when you have a nuclear power plant, this nuclear power plant will produce neutrinos. And what we do is to detect these neutrinos coming from the nuclear power plant and to try to understand them in the properties. And for that purpose, we have, I'll show you this slide is more simple. You have a nuclear power plant, then we place two detectors. The first one is 400 meters from the nuclear power plant, and the second one is more than 1 kilometer. So our goal is to detect neutrinos reaching the first detector, the near detector, and then to detect them again, reaching the second neutrino, the second detector. And in this distance, as we saw now, that they will oscillate, they will change the flavor. So since they will change the flavor, this means that since our experiment is sensitive only to one flavor, so the number of neutrinos that will be detected at the far detector will be less than the number detected at the near detector. And this difference is what you call the dispersion. And this dispersion, if you calculate it, if you measure this dispersion, you can measure some other things, some parameters of the matrix I showed you before. And this is the goal of our experiments. Okay. So now, how do you detect neutrinos in our case? I have a call again. Sorry. Just to stop it. Okay. How do we detect neutrinos? When you have a nuclear power plant, inside of it, you have what we call the beta decay. I don't know if everybody knows about beta decay. Maybe I would say a few words during the questions. And the beta decays is a transformation of a neutron becoming a proton. And when a neutron becomes a proton, this process will be accompanied by an emission of an anti-electron neutrinos. This is the first line of my slides. This new E with a bar below, above, is what you call the anti-neutrino. So these are the neutrinos coming out from the nuclear power plants. And then they come out, so they reach our detector. Our detector is full of hydrogen, okay? And as you know, hydrogen atom is just a proton alone with an electron turning around this proton. And this means that it's full of protons. And then these neutrinos coming from the nuclear power plants plus the proton, this means interact with the proton, will produce two different particles. We produce the E plus, which is the positive electron that we call the positron, and a neutron. Okay. So what we do in our experiment is to detect this positive electron, E plus, and this neutron. So if I see in my detector, if I detect the E plus and the neutron, I can be sure that there has been a neutrino which entered my detector and interacted with a proton of my detector. This is what we do. So the E plus and the neutron are the signature of the presence of a neutrino interaction inside our detector. Okay. And the E plus will be the first one to be detected. We call it the prompt signal. And the neutron will be the second one to be detected. And we call it the delayed signal. So these two coincidences, these two particles form the signature of a neutrino interaction. This is what we do in our experiments. Just to show you the detector I'm talking about, it's a very, since I remember that I said to you that neutrinos interact very, very weakly. So if you want them to interact, what you have to do is to build huge detectors, okay? So this detector you see here is 7 meters high, 7 meters high, and about 4 meters for the large. So this is huge. So we have two like this, the first, the near, and the other one is the far detectors. So in these detectors is filled by liquids that we call the scintillator, in which there are these protons which allow the neutrinos to interact and then to be detected. So they are very huge, 7 meters high and 4 meters large. This is because you want to maximize the probability of interaction of neutrinos inside of your volume of detection. So I wanted to see you so the last thing, because otherwise I'll be very long. This. So I detect all my neutrinos, and as you can see, I want you to see the the picture which is at the bottom, okay, bottom left. in this picture, you have the observation and the oscillation prediction. So if there is no oscillation, this means the amount of neutrinos that reach the far detector is the same amount that have previously reached the near detector. This is in the case there is no oscillation. So if you do the ratio of these two amounts, you have to find 1, okay? Because if there is no oscillation. And then you see the blue line, the blue dotted line, you see the line we expect, we should see if there was no oscillation at all. But you see in red, the real line we have from experiments, you see that we are below 1. This means that from the near detector to the far detectors, neutrinos have changed. Since we are sensitive only to one flavor, so we measure at the far detector only a fraction of the total neutrinos we had at the beginning. So this is the proof again of the oscillation. So neutrinos from nuclear power plants also oscillate, means they change also flavor. And thanks to this, we are able to calculate what is the amplitude of this oscillation. And the amplitude of this oscillation is given by this particle function, which is the sine square of θ13 angle, which is the angle that I showed you when I showed you the parameters of the matrix. And the last value we found our experiments, and we published the paper about this in Nature. Maybe I will send you the links for those who want to read more about this. So this is in very short, what I do and why we have to think and to try to understand again more and more about the neutrinos, because they are very, very important in our understanding of the universe. And the last thing I want to say to you is, maybe some of you have heard about what we call the dark matter. Dark matter is a very special matter in the universe. It's the most abundant matter in the universe. It's more than 90% of the matter in the universe, but we are still unable to detect them or to know what is the composition of this dark matter, simply because they are very weakly interacting. If you want to detect something, this thing must interact with something else, then you can detect. So if there is no interaction, you cannot detect it. And this is the case of the dark matter, which is weakly interacting particle, weakly and massive. We know that they are weakly interacting, but massive. And if you see weakly interacting and massive, you think about neutrinos. So neutrinos could be candidates to the dark matter. Maybe dark matter is composed of neutrinos, maybe. So you see that many questions like this are of interest for physicists to study neutrinos. I will stop here and I say thanks.
I have a question, Professor.
Okay, give me 1 second to come back to the. Okay, tell me.
Okay, so I have. Are there any applications with this? Are there any neutrino application except for the production of electricity, right?
Yes. This is a very
Yes,
good
are
question.
they?
Okay, you have more than one question?
No,
Okay.
not yet.
Not yet. Thank you. It's Mosa. Thank you, Mosa. This is a very important question, and that's you want to know about the applications, and there are many applications, and maybe I will show just one. Okay. Remember that I want to see the slides. Okay, this slide, for example. Okay, you see in this slide, I've got my detector, okay, which is not far from the nuclear power plant, and I detect neutrinos coming from the nuclear power plants. The energy of these neutrinos, the orientation of the neutrinos, and other properties of these neutrinos coming from the nuclear power plants depends on what is the nuclear fuel inside of the reactor. It depends how is this nuclear fuel enriched. It depends how are these nuclear power plants, at which power is it operating. So this means that the simple fact of measuring these neutrinos coming from the nuclear power plants is telling me how is the inside of the nuclear power plants operating. You see, I can have information about the core of the nuclear power plants. This is the way. That's why in my research, I work for the International Agency of Atomic Energy, because thanks to neutrinos detection, I can, without entering the nuclear power plants, okay, without doing any measure inside, just from outside, thanks to the neutrino detection, I can know very important information about the inside of the nuclear power plant. So I can know, I can predict the controls, I can measure the power, I can measure many other things about the nuclear power plants. And this becomes very, very important. Okay. So as a tool, if you want to do inspections of nuclear power plants, if you want to control, if you want to know what's happening inside of the core, so you have nuclear applications that are linked to neutrinos measurements. Very important. Is it clear for you, Musa?
Yes, thank you.
You're welcome. The
Professor,
rest
we
still
have
there?
another
There is
question in the chat box.
there was a question in
Yeah.
the chat.
Alfred is asking if the neutrinos can travel at the speed of light.
Ah, almost, because if you want to travel at the speed of light as particle, you have to be massless, like a photon. A photon is massless. That's why it travels at that speed. So if you want to travel at the same speed, you should be massless. As you have seen in my presentation, the neutrino have got mass, so they are traveling almost, because the mass they have is very, very low. The first indications are giving us the threshold that it may be less than 5 eV, you see, electron volts, so it's very low. So it travels at very high velocity, close to the velocity of the light, but it's not exactly equal. Simply, they have mass. When you have mass, from the physics equation, you cannot reach the the light velocity. Another question in the chat. I don't see the chat. I don't know where's the chat. Let me see. More option.
Yes,
Okay.
it's in
Ah,
the right in the bottom. You have a
okay.
little bubble.
I've seen it. Fine. Okay. Ah, yes. About this. Yes, neutrino can travel, but since they have mass, they will have a velocity close to the c value. 3 times 10⁸ per second. But this is only possible if you are massless, like a photon. So they'll be traveling very close, but not exactly equal.
I have another question.
Yes, Musa.
Is there a way that because you mentioned that you're an experimental scientist, right? Is
Yes.
there another way that we uh, students can be able to put this concepts into practice?
Mm. What do you mean by practice?
I mean, like, are there projects available where it's like you can where there are competitions where students can like be able to participate and give out and put the concepts of the neutrinos into basically just be
Yes.
experimental scientists, even if it's for a day.
Um, I mean, I understand your question, but it's not easy. I mean, I have to think about. It's a very good question for me. I have to think about how to put this in practice for students, for example, to see something or to detect something with a very small. Um, 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 I mean, just to show people maybe the applications. This is very different for neutrinos since you see that my detector are very huge. Okay, they are 6, 7 meters high, so I cannot bring it to you. Uh, so if you have a very small detector, you will not see the neutrino because they are very weakly interacting. You need to have huge detectors. For other particles, there exist these very small detectors, so you can use it for practice to see something. But in our case, it's very difficult. But maybe if you want an exercise, you just if you know a little bit how to program in C++, for example, you can be given some data, okay, about neutrinos, and try to do some pictures, some to do some for some slides, I mean some plots, showing the energy, showing the direction of neutrinos, and showing the spectrum of the neutrinos, something like this. This you can do it if you have just C++ notions, and I can provide you the data so you plot the properties of the trainers. This can be done as an exercise for you.
Oh, okay. Thank you.
You're welcome. Are you can you program in C++ or Python, for example, Mosa?
Yes, but it's not very strong. But I did a course in C++ and Python in year 1 and 2, respectively. So I would have to like go back and
Mm-hmm.
and
You had
do.
a course, but did you code yourself? Have you ever coded something? Maybe just a simple equation, for example, second order equation. Try to program it and to do it. Have you ever done something like this, for example?
I've done that in numerical analysis. Um, with
Hmm.
Ranjakuta method to
Okay.
yeah,
Window for
yeah,
approximation. Okay.
for
This is good.
approximate. It did not work out well, but it worked for the first values, and then the next I didn't understand what was happening.
Okay. So
Yeah.
we can. I mean, it's very important for you now, for as scientists, you see, we can no more do science without at least programming. Okay, because it's a new language now, so you have to take your time also to handle these tools of programming. It's very important because you're gonna do it, even though you go in theory or you experiments like me. You need programming to do many things in science. So you have to put it inside of I mean among your project to handle programming. You can use Python if you want or C++, even though my advice for you is to begin by C++, but you can also learn Python because many softwares that you're going to use in particle physics or in science are written in some language. And this language is either Python or C++. And you need to know how to program. It's very important.
Yes, I did notice, because most of I'm currently doing a project on in quantum mechanics, and I was told that I'm going to need to do a simulation first. So we do need the tools.
Yes, and other
Yeah.
simulation softwares are written in C++ or Python or some other language. So you need to know this.
Yes,
Very
yes, Prof.
important. Okay, another question. Alfred is not asking, speaking. Alfred is still there. Alfred, are you there? I see also Bob. I don't know if Bob is there. Alfred is there. Alfred, do you have any question?
I don't have any questions for now. Thank you very much for the presentation. It was wonderful.
Thank you. You can have my mail from Dora, so we can continue talking and trying. Even if you want, we can have a common project about neutrinos and something like this, so we can continue discussing even after this this talk.
Oh, okay, thank you so much.
You're welcome.
I'll
Bob
put
is
the
there?
video at the end on the WhatsApp group you have, and I will send you to the email of Professor Kali and Dr. Ska.
Oh, perfect. Bob is there. Bob is not speaking at all. Bob.
I don't have any question right now.
Okay, tell me. You don't have any questions for right now. You don't have. Okay.
Okay. On the last note, on the very last note, in just a minute, can you just tell us just a bit about the Higgs boson particle? Higgs boson.
Higgs boson. Oh, I just said, I mean, in this slide you see here. Can you see my slide? Can you see my slide?
Yes, we can.
Yes. Then you see in the far right, on the top, you have this H, which is the Higgs boson particle. It's a very important particle that has been discovered in 2012 at the CERN. It was predicted 50 years before by Higgs, Booth, and Englert. They were free to discover this particle. That's why, first of all, as physicists, we don't really like to call it Higgs boson, because it's not fair for the other two guys. So we call it the scalar boson, or we have to say the Higgs, Booth, Englert particle. You know, Englert is from Belgium, so Belgian people used to say Englert particle. So it's depending on the country.
Yeah,
so
sorry, Belgian people are always a bit weird.
That's why we say the scalar. So what is the Higgs boson? When you're gonna see, maybe not today, but today you're gonna have time and experience enough to study the standard model, you will see that when you write your questions at the beginning, okay, you write the questions of how does the particle should interact, okay, and this question is what we call the Lagrangian. Lagrangian is the question which contains the interaction of the particles. And this Lagrangian, if you put mass, if you give mass already, you say that all your particles will get mass, this Lagrangian will not work. You're going to have some problems of symmetries. So what you have to do is at the beginning, you say all the particles have got no mass. Then the equation works to some point. And then from that point, you need now to give mass to your particles if you want to do the calculations. And then the question was, how do particles get mass? And Booth, Englert, and Higgs suggested the existence of a field that we call the Higgs field, and say and demonstrate mathematically. Just it's not just you say, you know, you are in physics. When you say something, you have to why the question is going with this. So they demonstrated that if we say there exists a field that we call the Higgs field, and it's the interaction of a particle with this field which provide mass to this particle. And then it works. I'm sorry, the baby's there. It's again there. Give me 1 second. Hello, ta maman.
This is the real life, huh? So we will just wait for him.
I was saying, so the Higgs field is the field whose interaction provide mass to particles. And for each field in physics, there is a particle corresponding to this. So the Higgs boson is the particle corresponding to the Higgs field. This is just like imagine a I don't know, a football game, for example. Okay, people coming after the football game. You see, you have a crowd of people. Then you have to pass through this crowd of people. Okay, if it's me or Mosa, okay, we're going to traverse without any interaction. Okay, we're not attracting people on us. Okay, we just traverse the crowds. But if it's, I don't know, LeBron James, okay, or I don't know, Ed Sheeran, if you want to traverse the crowd, people will be attracted by this guy, okay? People will want to touch him, to come close to him. And the amount of interaction with this crowd is the equivalent of the amount of interaction with the Higgs field of a particle. The more you interact, the more you have mass. So this is something that you can imagine like this. So the more you interact with the field, the more you interact with the crowd, the more you have success, the more you are known. Yes, the same thing for particle. The more it interacts with the Higgs field, the more it will get mass. So Higgs boson is very important because it's the particle which is responsible of mass of particles, and it also interacts with itself. That's why it has got mass, and it's 125 GeV mass. Very important. Are there any people? I see 2 other people, but I don't see the names. I see Musa, Bob, Alfred, but I don't see the 2 other people. Is there any question? Any other question?
We have Sia and Lawrence.
If you don't have questions, I will ask you questions. So you better ask me. Otherwise, it's me who's gonna ask you.
I'm sorry, I arrived late for this presentation, and I've learned not much, but I think this is an interesting topic. Most of the question, one of the questions that I had, Musa already asked it, and thankfully you answered it very well. So I think I need to do some more researches, and at least I'll have more questions by then.
Okay, no problem. Okay, we can continue discussion even by mails or WhatsApp and so on. It's okay for me. So maybe it's my turn to ask questions. One question for each of you. Are you ready? Mosa, are you ready for my question? Mosa, are you ready? Are you there? Are you still there?
Sometimes the Wi-Fi is not stable, so sometimes yeah,
Sometimes
they have to get up and come back. I don't know if it's this case now. Oh, maybe they're afraid of your question.
Or maybe they don't want to say, here I am for my question. Okay. Okay.
Yeah, they disconnect and they will come back, I think.
Maybe.
And we can wait just a few seconds.
Yes.
Or maybe you can put a general question in the chat or something like that, and if somebody can have the answer, or it's a collaborative answer, maybe they can help each other. Oh, yeah, Mosa is there again.
Okay. Okay. My question is this. I mean, it's a very just. The first question is, what the difference between mass and weight for you, Mosa?
For me, oh, okay. Well, the difference between mass and weight is that weight is the mass multiplied by the gravity, and mass is a property, I think.
What is mass alone?
Mass isn't it a property of matter?
Like charge, like color. So it's not very special. I mean, it's not very precise yet. Mass also, color also is a property, like charge or anything. I want something very specific.
You want something specific?
I mean, more than saying just a property. What is particular for mass? Because if you say to me just property, so I can say the same for color, the same for charge, the same for size, and so on.
Oh, okay. Okay.
What is mass?
I just know it as that. Can I get a moment to like it has like it's I just know it as a property of matter.
I say you're right. But
Yeah.
not as yet. If you say just property of matter, I can say also the same for the color. Color is property of matter. Size also is a property of matter. I don't know, the shape also of the matter is a property of the matter. You see, but what is mass specifically?
Well, the other thing I can say is that it has like we have quantities, but then you're going to say we also have quantities in charge and.
I see.
So I'm just trying to think of properties of mass, but then you're going to say that charge also has that, and color also has that.
That was the goal of my question. You see that some in physics, in reality, the things that we know the best, okay, we naturally know, okay, what is mass, and the things that we know the best are the more difficult to define. You see.
Yes, it's very like it's now like weird or something that I don't know the explanation of mass.
So a sub question: is mass constant? Is it a constant quantity?
Yes.
It never changes.
Hmm.
Hmm.
Yes.
Yes. I'm not sure because according to Albert Einstein, the mass can change when you are moving excessively quick with velocity close to the one of light. You see.
Oh, the E equals to mc squared.
Yes.
The one that changes there is because, oh yeah, yeah. Oh God.
And you have this question. We say m. I mean, the mass in motion is different from the mass at rest. In
Yes,
yes, it's only when you are moving very, 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 very.
yes.
Um,
The change in energy is due to the change in mass. So mass is not constant.
yes. See?
Okay.
Okay. Question for Alfred. Alfred, what is the difference between energy and work? If Alfred is still there.
The difference between energy.
Between energy and work.
Well, I think energy is a property of matter. I don't know, but um, I believe, or I think I know that matter has